My name is Chelsea LeBlanc, and I'm a junior in the computer science program here at the University of Michigan. Through the SURE program, I've been working this summer in the Advanced Computer Architecture Laboratory under Professor Austin and Professor Bertacco, as well as with PhD student Joseph Greathouse on a software security project titled A Virtual Machine-Based Sampling System for Dynamic Software Analysis. First off, I'll give you a little background on the type of security flaws that we're looking to protect against. Many types of software take data from a network connection and use that data internally. For example, when you log into your email or any other internet account, you are giving it a username and a password, which are used across a network connection to give you access to your account. But let's say that instead of just giving it a username in the provided space, you also type in some malicious code. If the software is not secure, it may log you in using the good username and password you provided and then execute the bad malicious code without setting off any alerts. You could see that it might be beneficial if the software didn't automatically trust any of the data that comes across a network connection, but would rather mark it as tainted, meaning that it could represent a possible security threat. If the software then noticed that it was about to use any of the tainted data to execute code, send a query to the database, or even access a memory location, it would signal an alert. Some runtime protection programs that do this sort of security checking do currently exist. You may be familiar with such utilities as Valgrind, Rational Purify, or even DinInst. None of these utilities are suitable for protection on an average user's computer, however, because they all incur very heavy overheads and create large slowdowns in the system. Such security measures as these are really only suitable for developers and test scenarios. Our goal in the project was to create a software implementation of a system that could track taint propagation without incurring drastic overheads, such that it could be used on the general user's computer. Our solution was to create a system that would be distributed over a population. That is, the taint tracker would be run on many systems, with each instance only monitoring a small portion of each. For example, a piece of software might be distributed to a large number of households in a user population. For each household, only a small percentage of the program would be monitored using our security system, and since the overhead would be so low, all the users could run at full speed. If the system then identified potential problems in the small portion being monitored in any of the households, then these vulnerabilities could be reported back to the developer before they're actually exploited. With the main goal of the project in mind, we can move on to the implementation. The precursor project to this one, also implemented by the same team, was implemented entirely in hardware. On the other hand, our implementation was done purely in software. So as you can see here, our entire system runs on top of a hypervisor called Xen. A hypervisor allows you to run multiple operating systems on the same machine. Like here we have Linux, another instance of Linux, and Mac, all running on one Xen hypervisor. It's very similar to Microsoft Parallels if you are familiar with that piece of software. Additionally, for our implementation, we used a processor emulator called QEMU. What QEMU does is to really replicate each basic instruction that would normally be executed by the hardware, by instead completing each step of the instruction by hand in software. This allows us to keep track of all intermediate values of variables and registers, as well as some associated metadata. Metadata gives us additional information about each variable. So, for example, we could keep track of whether a variable has a tainted value or not, and that would let us watch how tainted values propagate through the system. So in the example shown here, we see that some data is being passed in through the network and read into the variable x. The red asterisk represents some metadata about x, in this case marking the variable as tainted because it came over a network. When the next instruction, which is setting the variable of y, is executed, you can see that y is dependent on x, which is tainted. Thus, the taint is propagated and y is also marked as tainted. The same holds true for z. Because z relies on x, it is also marked with tainted metadata. Whenever we want to do something like this, as in following the propagation of tainted data throughout the system, we need to run the program inside QEMU so we can emulate each instruction. So, to show you the bigger picture, we have Xen, our hypervisor, running on the base level. On top of Xen, we have two more domains running. All network contact with these domains must first go through Xen, So Xen is basically like a buffer to the outside world, interpreting any and all signals or inputs. So under normal operation, when no tainted data is present, a system will operate in the user domain, which we call domain U. The program, its variables, and registers will all be running here. So if a network connection comes along and tries to send in data, Xen will mark this value as tainted, and all values and registers in domain U will be copied over after the domain is paused. Once these values are copied over into domain 0, where we have QEMU running, QEMU will monitor in taint propagation mode to see if the taint variable is ever used in an inappropriate way. So, for example, memory accesses or instruction execution. If so, a signal is sent back to the developer and a vulnerability is marked. If not, the program will return to normal operation in the user domain after a marked period of time, and normal operation will resume. So, in closing, our system is still under development, but it is on track to be submitted at the ASPLOS conference by the end of the month. The past 12 weeks of working on this project has really been a great experience and has introduced me to many of the latest issues in computer science. Thank you for your time.